Welcome to all of you in this YouTube channel of GATE classes, which is a great initiative by the TEQIP faculty members. Being a faculty coordinator of electromagnetic theory, I am going to conduct the lecture number 13, and the title of the topic is Transmission Line Part 2, in which I am going to discuss the numerical problems based on transmission lines, the theory which we have already covered in the last lecture, what is ideal transmission line, what is distortion-less transmission line, and what is a lossless transmission line, what are the conditions which has to be satisfied in order to make a transmission line either lossless or distortionless. So let's have a problem session on that concept. This is problem number 1. An air line has Z0 is equals to 70 ohm and beta phase constant 3 radian per meter at 100 megahertz. Calculate inductance and capacitance per unit length of the line or per meter length of the line. Now here we have to understand the line is nothing but an air line. So it is a lossless line basically. And when the line is lossless, it means resistance of the conductor is 0 and conductance of the dielectric is 0, because we have studied the model of the transmission line, because transmission line is a distributed network, it is not a lumped network. But for simplifying the things, we have just assumed this is one part of the transmission line, and this is resistance of the conductor, inductive reactance of the conductor, conductance of the dielectric, and capacitive susceptance of the dielectric. So this is the model of the transmission line. When the line is air line, it means it is lossless. ठीक है, तो इसको लॉसलेस कहने की जरूरत नहीं है, चूंकि ये एयर लाइन है तो लॉसलेस लाइन है. लॉसलेस लाइन है यानी रेजिस्टेंस ऑफ द कंडक्टर जीरो, कंडक्टेंस ऑफ द डाइलेक्ट्रिक जीरो, तो आर और जी हमारे जीरो हो गए. और जैसे ही आर और जी जीरो हो गए तो सिर्फ लाइन में क्या है, इंडक्टेंस एंड कैपेसिटेंस. मींस आई कैन ड्रॉ द मॉडल like this, and this is the model. With the help of this model, this is j omega L and this is j omega C. With the help of this, now we want to solve this particular problem. Now airline has having a characteristic impedance 70 ohm. So in the last class we have derived the characteristic impedance. The standard characteristic impedance is Z is equals to R plus j omega L upon G plus j omega C. But of course, when the line is lossless, R and G are 0, so it is L by C. So Z0 is equals to L by C, root over L by C. And this Z0 is given to us, how much it is? 70 ohm. Now, let us talk about beta. In a lossless line, alpha is 0. We have just derived in the last class. And what is gamma? When alpha is 0, gamma is simply J beta. And what is beta? Beta is nothing but omega root LC. So when I compare beta only, gamma is equals to J beta is equals to J omega under root LC. But if I write beta only, this is omega under root LC. Now beta is given to us, omega frequency is also with us, and root LC हम यहाँ से निकाल सकते हैं. यानी हमारे पास इक्वेशन आ जाएगी under root over LC is equals to beta by omega. And what is beta? Beta is a phase constant 3 radian per meter, which is given to us. Okay, and omega is 2 pi f. What is the frequency here? 100 megahertz, means 100 into 10 to the power 6. And I can better write this particular expression 3 into 2 pi into 10 to the power 8. Okay, now I am having two equations. One is Z0 is equals to root L by C is equals to 70 ohm. Another one is root over LC is equals to beta by omega is equals to 3 upon 2 pi into 10 to the power 8. This is equation number 2. And with the help of these two equations, it is very much clear. If I multiply these two equations, let me write what I will get. Root L by C is equals to 70 ohms, and under root LC equal to under root LC is equals to 3 by 2 pi into 10 to the power 8. I can also write 3 by 2 pi into 10 to the power minus 8, no issue. And this is equation number 1 and this is equation number 2. If I multiply these two equations, then definitely root C cancel, and I will get L, because root L into root L is L, and this L will be 73 ja 210 divided by 2 pi into 10 to the power minus 8 Henry per meter. This will be the inductance. And if I divide equation, this is the result of equation 1 multiplied with equation 2. And if I divide equation 2, equation 1 in equation 2, okay, because that is root over LC and that is root over L by C. When I divide second equation divided by one equation, when I write this, then root L will cancel and the C will be equal to 3 divided by 2 pi into 70 into 10 to the power minus 8. Capacitance unit क्या है? Farad per meter. If you calculate these values with the help of calculator, of course, okay, then you will get the inductances. I am directly writing the answer. Please check with the help of proper calculation, with the help of virtual calculator or uh, calculator which you are having right now. L is equals to 334.2 nano Henry per meter. This is the inductance. And as far as the capacitance is concerned, this capacitance is 3 upon of course 3 upon 2 pi into 70 into 10 to the minus 8 और सॉल्व करने पे ये जो आ रहा है this is 68.2 picofarad. ठीक है, so I am writing the simplified expression over here. It is 68.2 picofarad per meter. So in this way we can determine the inductance per unit length of the transmission line and capacitance per unit length of the transmission line for a lossless line or for a air line. ठीक है, so the problem is very simple. जो डेटा हमें दिया है उसको यूज करना है, जो डेटा हमें निकालना है फॉर्मूले में वो फिट बैठ जाए. तो आप अननोन पैरामीटर नोन पैरामीटर्स आपको पता है, फॉर्मूला यूज करके हम प्रॉब्लम को सॉल्व कर सकते हैं. ठीक है, let us have another problem which is based on distortion-less transmission line. Let me read the problem. A distortion-less transmission line has a characteristic impedance 60 ohm, alpha attenuation constant 20 millinepper per meter, U is equals to 0.6 C. It means the velocity of electromagnetic wave in that particular distortion-less transmission line is basically 60% of the velocity of light. And we know that what is velocity of light? 3 into 10 to the power 8 meter per second. So the 60% of that is nothing but 1.8 into 10 to the power 8 meter per second. And we have to find RL, GC and lambda at 100 megahertz. Means the frequency of operation is 100 megahertz, again 10 to the power 8 hertz, and we have to calculate the various parameters of the transmission line like resistance, inductance, conductance and capacitance. We know that resistance and inductance are making a series impedance and conductance and capacitance are making the shunt admittance of the transmission line. We have to calculate all these four, as well as lambda means the wavelength of the electromagnetic wave which is to be travel in the transmission line, which is a media basically. So here I have to apply the formula of the distortion-less transmission line. In the last class we have seen that for a distortion-less transmission line, general value of the characteristic impedance is Z is equals to Z0 is equals to R plus J omega L upon G plus J omega C. This was derived in the last class. ठीक है, ये हमने पढ़ा था. But this is a general expression of the characteristic impedance. But basically, when we are saying the line is distortion-less, which condition has to be satisfied? LG equal to RC. और जैसा कि मैंने आपसे कहा था, इस कंडीशन को हम कई प्रकार से लिख सकते हैं. L by R equal to C by G, ठीक है, या R by L equal to G by C, whatever, जो भी जरूरत पड़े उस तरह से लिख सकते हैं. तो ऐसा जब हम लिखते हैं तो हमने देखा था कि न्यूमरेटर से R यदि कॉमन ले लिया जाए, डिनोमिनेटर से यदि G कॉमन ले लिया जाए, तो ये बचेगा हमारे पास 1 plus J omega L by R, और ये क्या हो जाता है 1 plus J omega C by G, and L by R and C by G are equal, so these two terms will cancel out each other. So we have Z0 is equals to R by G. But I can also write root over R by G. From this relation LG equal to RC, you can very well write R by G is nothing but L by C. So I can write root over R by G equal to root over L by C. So again I am getting the same kind of result. The characteristic impedance of a distortion-less transmission line is also Z0 equal to root over L by C or root over R by G. And again we are getting the same conclusion that the imaginary part of this particular impedance is missing. It means R0 is existing, but what about X0? X0 is 0. So in the characteristic impedance of the transmission line, basically there is no imaginary term. There will be no characteristic reactance. There is only a characteristic resistance. तो ये हमें पता है. देखिए Z0 बराबर 60 ओम हमें दिया है. Means I can write one equation z naught equal to root over r by g is equals to root over l by c is equals to 60 ohm. Okay, let me write this is equation number 1. Now alpha, the attenuation constant of the transmission line, we can talk about that. So alpha attenuation constant जो है, we have derived in the last class, and that alpha attenuation constant root rg, it is given in the problem, and that alpha is 20 millinepper per meter. So we can substitute its value over here, 20 into 10 to the power minus 3 nepper per meter. So we are having this relation. And u means the velocity of electromagnetic wave in the transmission line, that is 0.6 times of the velocity of the light. So we have u is equals to 0.6 c, 0.6 c, and that is 0.6 into 3 into 10 to the power 8 meter per second. Means I can write velocity of the electromagnetic wave in distortion-less transmission line, it is 1.8 into 10 to the power 8 meter per second. And we have derived in the last class this velocity u is none other than 1 upon under root LC. So I can write 1 upon under root LC is equals to 1.8 into 10 to the power 8 meter per second. One relation we already got, z naught equal to root over r by g is equals to root over l by c is equals to 60. Okay, 60. So let me write, this is equation number 1, and this is equation number 2, and this is equation number 3. And with the help of these three fundamental equations or relation, we have to find out the various parameters of the transmission line, which are resistance, inductance, conductance of the dielectric, capacitance of the dielectric, and wavelength of the electromagnetic wave at a particular frequency, and that frequency is none other than 100 megahertz. You can better write 10 to the power 8 hertz. Okay, तो आइए देखिए कैसे करते हैं. Question 2 or 3. Again, if I multiply 2 and 3, what I will get? U z naught is equals to, तो देखेंगे रूट एल कैंसिल हो जाएगा, ठीक है, रूट एल बाय सी under root L by C into 1 upon root LC. So this will be root L cancel 1 upon C. So I am getting U z naught equal to 1 by C. So with the help of this relation, shall I write C is equals to 1 upon U z naught? Now U I am having, Z naught I am having. So with the help of equation 2 and 3, you can substitute the value of U and Z naught in the equation number 4, and you can very well calculate the value of the capacitance per unit length of the transmission line with the help of equation number 4. Okay. C is equals to 1 upon U Z naught. Let me substitute the values for simplification. U is 1.8 into 10 to the power 8, 1.8 into 10 to the power 8, and Z naught. How much Z naught is? Z naught is 60 ohm. Okay, let me put the value 60. This value is in farad, and of course you can convert into the picofarad or nanofarad, whatever it is. Okay, so this is the capacitance. As far as the inductance is concerned, let me divide. Let me divide the equation 2 and 3. Okay, let me divide 3 by 2. Okay, z naught by u. So if I write z naught by u, this is basically under root L by C divided by 1 by root LC. So you can better write root over L by C into root LC. Root C cancel, it is L. So basically the value of the inductance is nothing but characteristic impedance upon U. U means phase velocity of the electromagnetic wave in the transmission line. And of course, the transmission line for which we are talking about is the distortion-less transmission line. So what is the value of Z naught, characteristic impedance? It is 60 ohm given. And what is the value of U? We have just determined 1.8 into 10 to the power 8 meter per second. And again, you can convert this value of inductance in nanohenry, picohenry, okay, whatever is convenient to you. Let me write the answer of this particular problem. The value of the capacitance as far as capacitance is concerned, the value of the capacitance is 92.59 picofarad per meter. Please check the values with the help of virtual calculator. Value of the inductance. The value of the inductance after solving this particular expression, it is 333 nanohenry per meter. So this is the value of inductance and this is the value of capacitance. And alpha is also given to us. Alpha is equals to root Rg. Okay. Alpha is equals to root Rg. alpha is equals to root RG, and that alpha is given to us. How much it is? Alpha is 20 millinepper. Okay. रूट आर जी को देखिए, मैं एक रिलेशन यहाँ पे अभी आपसे कहा था कि एल जी बराबर आर सी इज अ कंडीशन ऑफ द ट्रांसमिशन लाइन, डिस्टॉर्शनलेस ट्रांसमिशन लाइन. So you can write in place of G, you can write RC by L. Okay. Here I can write LG equal to RC. So let me write the value of G. I can put RC by L. Okay. Value of G is equals to RC by L. If I solve this, alpha is equals to root R into root R means R under root C by L. और इसको यदि मैं थोड़ा सा सिंप्लीफाई कर लूं तो अल्फा इज इक्वल्स टू आर और रूट सी बाय एल. इट इज नथिंग बट 1 upon z naught because z naught equal to under root L by C. So I can write alpha is equals to R by Z naught. With the help of this, I can get a conclusion that the resistance of the transmission line conductor is nothing but attenuation constant multiplied by the characteristic impedance of the transmission line. So R is equals to alpha Z naught. So you can put R is equals to alpha Z naught. Now the calculation is quite simpler for us because alpha we already know 20 millinepper per meter, 20 into 10 to the minus 3, and Z naught is also with us. How much it is? 60, I think. Let me check once again. Yes, it is 60. So we can multiply this. R 20 into 60 is 1200. 1200 divided by 1000 is none other than 1.2. So the value of the R is 1.2, of course, ohm per meter. Now the conductance value is remaining. Okay. Conductance value, how can we write? Because alpha is equals to root Rg. When I am saying alpha is equals to root Rg, now R is with us. So I can write alpha square is equals to Rg. So what is the value of conductance G? G is nothing but alpha square by R. Now alpha is with us. How much it is? 20 millinepper per meter. 20 into 10 to the minus 3 whole square divided by what is R? 1.2. So you can solve this value, and this value is exactly, it is 333 microsiemens per meter. Microsiemens per meter. So this is the value of conductance. As far as lambda wavelength is concerned, the velocity of the electromagnetic wave inside that particular distortionless transmission line U is equals to f lambda. Now we have to find out the lambda wavelength, which is quite simple, U by f, and the velocity we already determined 1.8 into 10 to the power 8, and the frequency is nothing but 100 megahertz. 100 megahertz means 10 to the power 8 hertz. So it will cancel out, and the lambda is quite simple, it is 1.8 meter. तो आप देखेंगे जो वेवलेंथ है, वेवलेंथ जो है वो छोटी आ रही है. ठीक है, जब वेवलेंथ बहुत छोटी हो जाती है और वो एक्चुअल लेंथ ऑफ द पैरामीटर लाइक रेजिस्टेंस, इंडक्टेंस, कैपेसिटेंस, कंडक्टेंस से कंपेरेबल हो जाए तो फिर वो हमारी लाइन लम्प्ड हो जाएगी, लाइन को हम डिस्ट्रीब्यूटेड नहीं मान सकते. ठीक है, सो हियर लैम्डा इज एग्जैक्टली 1.8 meter. Okay, so now I can conclude this. All the parameters are with us. Let me summarize. The value of the RLGC we have to find out. How much the R is. R we have determined. Okay, let me encircle so that you can get the answers in a simple manner. We have determined the value of C. Firstly, we have determined the value of C. How much it is? C is equals to 92.59 picofarad per meter. Then we have determined the value of L. How much L is? L is the 333 nanohenry per meter. Then we have determined the value of R. How much R is? 1.2 ohm per meter. And then we have determined the value of G. How much G is? G is equals to 333 microsiemens per meter. Then we have determined the lambda, the wavelength 1.8 meter. So all these are the parameters of the transmission line, distortionless transmission line, for which the problem is given to you. And the first problem also, we have determined the inductance and capacitance of the transmission line per unit length of the transmission line, for which the problem 1 asked. So I think it is clear to all of you. I made it clear both the transmission line, lossless transmission line and distortionless transmission line, with the help of these two examples. If you are having any query, you can put in the comment box so that I can resolve those queries as well. Okay, thank you very much. Thank you for joining us this particular evening and making this particular lecture successful.